Now in this video I am going to discuss about the electromotive force, that is small e, and terminal potential difference, that is capital V of a cell, and internal resistance of a cell, that is small r, and relation between the EMF, that is electromotive force small e, potential difference capital V, and internal resistance small r. Then I will go for the grouping of cells, that is cells in series, cells in parallel, then combination, that is mixed grouping, series also, and also in parallel. Also I will be discussing about the Kirchoff's law. There are two laws of Kirchoff's. Thereafter I will go for explanation of them. Now start from the electromotive force small e and terminal potential difference capital V of a cell. A cell is a device which creates a constant potential difference between the two ends of a conductor connected across it. As a result, a steady electric field is created and maintained in the body of the conductor, which is directed from its positive to the negative end. A cell works on the fact that a chemical reaction occurring in the electrolyte converts chemical energy into electrical energy. A potential difference is thus created and maintained between the two terminals, that is in bracket electrodes of the cell. Now what is electromotive force? EMF small e. EMF of a cell is defined as the maximum potential difference between the terminal of a cell in open circuit, that is when no current is drawn from the cell. It is the EMF of the cell which is responsible for pushing the free charge carriers, that is free electrons, through the circuit to constitute a current. EMF of a cell is not a force but the potential difference between the two terminals or poles of the cell in an open circuit. EMF can also be defined as the amount of energy required to take a unit positive charge around the circuit. The SI unit of EMF is volt. EMF of a cell is said to be 1 volt if 1 joule of work is done by the cell in driving 1 coulomb charge around the circuit. Now terminal potential difference, that is capital V. Terminal potential difference of a cell is defined as the potential difference between the two terminals of a cell in closed circuit, that is when a curve is drawn from the cell. It can also be defined as the amount of work done in taking 1 coulomb charge through the external circuit. Now there is some difference between the EMF and terminal potential difference. I am giving the picture, you go through it. Internal resistance of a cell, that is smaller. The opposition in bracket resistance offered by the electrolyte of a cell to flow of ions in bracket current through it is called the internal resistance of the cell. Because of internal resistance, a part of the energy supplied by the cell is dissipated as heat inside the cell. Internal resistance is not constant for a given cell but gradually increases as a cell is used. Internal resistance is always taken in series with the external resistance connected across the cell. It depends upon the following factors. Number 1, separation between the electrodes. It is directly proportional to the separation between the electrodes. Therefore, the larger the separation, the higher is the internal resistance, and vice versa. Number 2, temperature. Internal resistance decreases with the rise in temperature of the electrolyte and vice versa. It is because as the temperature rises, the thermal energy enhances the mobility of the ions also increases. Now number 3, nature and concentration of the electrolyte. As the concentration of the electrolyte increases, the internal resistance decreases. Number 4, area of electrodes. The larger the surface area of the electrodes immersed in the electrolyte, the smaller is the value of internal resistance of the cell. Now the relation between EMF small e, potential difference capital V, and internal resistance small r. Consider a cell of EMF small e and internal resistance small r connected across a conductor of resistance capital R to a key capital K. An ammeter and a voltmeter is also connected across the terminal of the cell. See the figure. Let I be the current in the circuit. Then small e equals to I multiplied by, in bracket, small r plus capital R, or small e equals to I into small r plus I into capital R. But IR equals to, we know that it is V. Therefore, small e equals to V plus IR. This is equation number 30 of the chapter Current and Electricity. Here IR is the potential difference across the internal resistance of the cell. Therefore, from equation 30 we can write V equals to E minus IR. Therefore, V we know is greater than small e. V equals to E if either I equals to 0 or R equals to 0. Therefore, R equals to E minus V by I. But I equals to V by R. Therefore, R equals to E minus V by V into R, which is equals to, in bracket, E by V minus 1 multiplied by R. This is equation number 31. Now the grouping of cells. The series DC circuits. The series circuits is the most basic of electrical circuits. All other types of circuits are elaborations or combination of series circuits. Figure is an example of a simple series circuit. It is a circuit because it provides a complete path for current to flow from the negative to the positive terminal of the battery. It is a series circuit because there is only one possible path in which current can flow, as indicated by the arrow showing the direction of electron movement. It is also called a series circuit because current must pass through the circuit components, the battery and the resistor, one after the other or in series. The circuit shown in this figure contains the basic components required for any circuit: a source of power, that is battery, a load or current limiting resistance, that is resistor, and a conductor, that is called wire. In this figure, this is another figure. Most practical circuits contain at least two other items: a control device, that is switch, and a safety device, fuse. With all 5 components in the circuit, it would appear as shown in this figure, which is a DC series circuit. Now, in the DC or direct current circuit, current flows in one direction from the negative terminal of the battery through the switch, which must be closed, through the load resistance and the fuse to the positive terminal of the battery. See, in this current and electricity, I have to give one very much important thing, which will give the conversion of each other, that is how the current is related to power, how the current is related to voltage and resistance and all that. I have not given till now. I am going to give you because just now I get in a book. So let us take this. Now to discuss the behavior of electric current in a DC series circuit, the figure is redrawn to include 3 ammeters and 2 resistors. Since an ammeter measures the internal resistance of the current flow, measure the intensity of current flow. 3 have been located in the circuit to measure the current flow at various points in the circuit. With the switch closed to complete the circuit, all 3 ammeters will indicate the same amount of current. This is an important characteristic of all series circuits. No matter how many components are included in a series circuit, the current is the same intensity throughout the circuit. While it is true that an increase in the number of circuit components will increase the resistance to current flow in the circuit, whatever the value of current flowing in the circuit, it will be the same value at all points in the circuit. Now, the first figure which I have given you, the current through resistor capital R1 is labeled I1 and the current through resistor R2 is labeled I2. If the total current in the circuit is I underneath small r, the formula describing the current flow is I small r underneath equals to I1 equals to I2. Now let us consider the resistors are increased to 5. The formula will be I small r underneath equals to I1 equals to I2 equals to I3 equals to I4 equals to I5. Without indicating how much current is flowing, it will always be true that the current through any resistor in a series circuit will be the same as that through any other resistor. Now the figure which I had given in a series circuit containing 2 resistances, in order to determine the amount of current flow in the circuit, it is necessary to know how much resistance or opposition the current flow will encounter. Thus, the second characteristic of series circuit is total resistances in a series circuit is the sum of the separate resistances in the circuit, stated as a formula. Thus, this becomes R small r equals to R1 plus R2. So, in this figure, this is R small r underneath equals to R1 is 5 ohm plus R2 is 10 ohm, or RT equals to 5 plus 10 equals to 15 ohm. The total resistance of the circuit is 15 ohm. It is important to remember that if the circuit were altered to include 10, 20 or even 100 resistors, the total resistance would still be the sum of all separate resistances. It is also true that there is a certain negligible resistance in the battery as well as in the fuse and the switch. These small values of resistance will not be considered in determining the value of current flow in the circuit. The Ohm's law formula for finding current is I equals to E upon R. Since the battery voltage is 30 volts and the total circuit resistance is 15 ohms, the equation becomes I equals to 30 volt by 15 ohms, that is equals to 2 amperes. Now the current flow in 2 amperes, that is in bracket, sometimes the word amperes is shortened to amps, and this value of current is everywhere in the circuit. To consider what effect of a change in resistance will have on current flow when the voltage remains constant, the total resistance is doubled to 30 ohms. Using Ohm's law, I equals to E upon R, therefore I equals to 30 volt by 30 ohm, that is equals to 1 ampere. It can be seen that current will be reduced to half its former value when resistance is doubled. On the other hand, if voltage remains constant and resistance is reduced to half its former value, the current will double its original value. That is I equals to E upon R, which is equals to I equals to 30 volt by 7.5 ohms, that is equals to 4 amperes. Thus, if voltage remains constant and resistance increases, current decreases. Conversely, if resistance decreases, current must increase. However, if resistance is held constant and voltage is doubled, the current flow will double its original value. If the voltage applied to the circuit, I am giving you the figure, is doubled to 60 volt and the original value of resistance is maintained at 15 ohms, I equals to E upon R, which is equals to 60 volt by 15 ohms, that is equals to 4 amperes. If voltage is reduced to half its original value with resistance constant, current will decrease to half its original value, that is I equals to E upon R, that is 15 V by 15 ohm, that is equals to 1 ampere. Thus, if resistance remains constant and voltage increases, current must also increase. If voltage decreases, current decreases also. It is important to distinguish between the terms voltage and voltage drop in discussing series circuit. Voltage drop refers to the loss in electrical pressure caused by forcing electrons through a resistance. The applied voltage, that is the battery, is 30 volts and is labeled ER, small r underneath. Since there are two resistors in the circuit, there will be two separate voltage drops. These two voltage drops will be the loss in electrical pressure used to force electrons through the resistances. The amount of electrical pressure required to force a given number of electrons through a resistance is proportional to the size of the resistance. Thus, the voltage drop across R1 will be twice that across across R2, since R1 has 2 times the resistance value of R2. The drop across R1 is labeled E1 and the across R2 is E2. The current I is the same throughout the circuit. Using E equals to IR, E2 equals to IR2, E1 equals to IR1, that is E2 equals to 2A into 5, E1 equals to 2A into 10, or E2 equals to 10 volt, E1 equals to 20 volt. If the voltage drop that is used across the two resistors are added, 10 volt plus 20 volt value equal to the applied voltage 30 volts is obtained. This confirms the basic formula for series circuit, that is ER equals to E1 plus E2. In any DC series circuit, a missing quantity such as voltage, resistance or current can be calculated by using Ohm's law if any two of the quantities are known. Now the figure is a series circuit containing three known values of resistance and a applied voltage of 150 volts. Using these values, the unknown circuit quantity can be determined by applying Ohm's law as follows. Consider R1 is 30 ohms, R2 is 60 ohm, R3 is 10 ohms, and RR equals to, we have to find IR, we have to find ER1, we have to find ER2, we have to find ER3, we have to find. Now take first of all the picture. Now total resistance R equals to R1 plus R2 plus R3. So it will be equals to 30 plus 60 plus 10, that is equals to 100 ohm. Now the total current IR equals to ER by RR. Now we know that ER is 150 and RR we got 100 ohms. So this will be equals to 1.5 ampere. Now voltage drop across each resistance E equals to IR. Using this formula we will get ER1 equals to IR into R1, that is equals to 1.5 amperes into 30, that is equals to 45 volt. Now ER1 equals to I small r underneath into R2, this is equals to 1.5 amperes into 60, which is equals to 90 volt. ER3 equals to IR into R3, that is equals to 1.5 volts into 10, which is equals to 15 volt. do these values for voltage drops equal to the applied voltage? Let us see. ER equals to ER1 plus ER2 plus ER3. We know that ER is 150 volts. Now let us see whether the left hand side is equal to right hand side or not. The left hand side is 150 volt, and we will add this ER1, ER2 and ER3. ER1 we got 45 volt, ER2 we got 90 volt, ER3 we got 15 volt. Now after adding we see that the voltage drop across the sum of the voltage drop equals the applied voltage. Now we have to solve various circuit problems which where Ohm's law will not so much applicable. However, it's applicable to everywhere, but it will be very much clumsy. But for that, law has come, law that is called a Kirchoff's law. Now, Ohm's law enables us to determine the equivalent resistance of a circuit, the current flowing through a part of the circuit, and the potential difference between any 2 points in a circuit when it is in a single source of EMF, and it can be reduced to a simple series and parallel combination of resistance. But it becomes very difficult to analyze a complicated electrical circuit using Ohm's law. Now Gustav Robert Kirchoff, a German physicist, in 1842 put forward a set of two rules which provide us the techniques to analyze or handle the complicated circuit. These are: number one, Kirchoff's first rule or junction rule. It states that the algebraic sum of the current meeting at a junction in an electrical circuit is always zero, or in other words, the sum of incoming currents is always equal to the sum of the outgoing currents at a junction. Now see the figure. Junction in a circuit is a point where the three or more conductors meet. Applying the rule at junction O, in this figure we find that I1 plus I2 plus I3 equals to I4 plus I5, or I1 plus I2 plus I3 minus I4 minus I5 equals to 0, or summation of I is 0. Hence current reaching junction O, that is incoming currents I1, I2 and I3 are taken with positive sign, and the currents I4 and I5 that leaves the junction, that is outgoing currents, are taken with negative sign. Thus the sum of all these currents at O will be 0. This rule is based on conservation of charge and reveals the fact that charge cannot accumulate at any point in a circuit. The total charge entering a junction in a certain time is always equal to the total charge that leaves it in the same time. Now second rule of Kirchoff's second rule or loop rule. It states that algebraic sum of changes in potential around a closed circuit loop is always 0. For applying the loop rule, we use the following sign convention. Number one is, if we traverse a closed loop, that is start from a certain point and move along the closed loop to return back to the point of start, bracket close, in the direction of current, the product of the current and the respective resistance, that is IR, counted negative and positive if move in the opposite direction. Number two, when traversing the loop, if we go from the negative terminal to the positive terminal through the electrolyte, the EMF small e of the cell will be counted as positive and negative when traversed from positive terminal to negative terminal. Number 3, equate the sum of steps 1 and 2 each to 0. Now let us apply the loop rule using the sign convention to the circuit. Loop A, B, MNA minus I1 R1 minus I3 R3 minus I1 small r1 plus e1 small e1 equals to 0. Therefore I1 R1 plus I3 R3 plus I1 R1 small r equals to e1. This is equation number 32 of the chapter current and electricity. Now loop BCD NB plus I2 R2 plus I2 small r2 minus small e2 plus I3 R3 equals to 0. Therefore I2 R2 plus I2 small r2 plus I3 R3 equals to E2. This is equation number 3 of the chapter current and electricity. Now applying junction rule at B, we find that I1 plus I2 plus I3 equals I1 plus I2 equals to I3. This is equation number 34. Now solving equation 31, 32 and 32, 33 and 34 simultaneously, we can find the value of I1, I2 and I3. These current can then be used for finding potential difference across various resistance. In the above circuit, we can also consider the loop ACDNA and apply Kirchoff's rules. Kirchoff's second rule is a consequence of the law of conservation of energy. As we go round a loop measuring various potential difference and return to point of start, we find that the algebraic sum of all the potential difference, that is net potential difference, is 0. Now very necessary to understand how to solve problems using Kirchoff's law. Now the first one is that draw a large circuit diagram so that there is enough room for labeling. Number 2, label each junction along with a few other points as A, B, C, etc. These are all in capitals for the identification of various closed parts, that is loops of the circuits. Now number 3, label all quantities, that is resistances, current and EMF. Assume the direction of each unknown current based on the fact that a current from a source starts from its positive terminal and flows through the external circuit to reach its negative terminal. If the actual directions of the current is opposite to what we have assumed, the calculated value of current will have a negative sign. Thus, correct use of Kirchoff's law not only gives the magnitude but also the direction of unknown currents. Number 4, use junction rule to express the current that reach or leave the junctions. This helps in minimizing the number of unknown currents in the circuit and hence reduces the calculation work. Now number 5, choose any closed loop of the circuit and travel around it to finally return back to the point of start. While doing so, write the potential differences across resistors, that is I into R, and EMF with proper sign, that is positive or negative, using Kirchoff's rules, and equate their sum to 0 to get an independent equation. Now number 6, choose more loops to get as many independent equations as the unknown current. Number 7, solve this equation simultaneously to find the unknown quantities. Portion of a circuit which illustrates Kirchoff's current law is shown in this figure. The current flowing through resistor R1 has an intensity of 4 amperes. The current flowing through resistor R3 has a magnitude of 1 ampere and is flowing into the same junction as the current through R1. Using Kirchoff's current law, it is possible to determine how much current is flowing through R2 and whether it is flowing towards or away from the common junction. This is expressed in equation form as I1 plus I2 plus I3 equals to 0. Now substituting the current value in the equation given, now I1 is 4 plus I2 plus I3 is minus 1, which should be equals to 0. Now I2 we get 1 plus 4, that is I2 equals to 5. Now we see minus 4 plus in bracket minus 1 plus 5, which is equals to 0. Now Kirchoff's current law find a wider application in more complex parallel or series parallel circuits. Now in the B of the figure is a DC circuit which is used to demonstrate Kirchoff's voltage law. The total resistance is the sum of R1, R2 and R3, which is 30 ohms. Since the applied voltage is 30 volts, the current flowing in the circuit is 1 ampere. Therefore, the voltage drop across R1, R2 and R3 are 5 volts, 10 volts and 15 volts respectively. The sum of the voltage drops is equal to the applied voltage is voltage of 30 volts. This circuit may also be solved by using the polarities of the voltage and showing that the algebraic sum of the voltages is 0. Consider voltage positive if the plus sign is met first and negative if the minus sign is met first when tracing the current flow. By starting at the battery and going in the direction of current flow, that is in bracket as indicated by the arrow bracket close, the following equation may be set up. Total voltage E1 equals to plus 30 minus 5 minus 10 minus 15, or E total equals to 0. The point to start around the circuit and the polarity to use are arbitrary and are a matter of choice for each circuit. Now we will go for the parallel DC circuit. A circuit in which two or more electrical resistance or loads are connected across the same voltage source is a parallel circuit. The parallel circuit differs from the series circuit in that more than one path is provided for current flow. The more paths added in parallel, the less opposition to flow of electrons from the source. In a series circuit, the addition of resistance increases the opposition to current flow. The minimum requirements for a parallel circuit are the following. Number 1 is a power source, number 2 a conductors, number 3 a resistance or load for each current path, number 4 2 or more paths for current flow. Now this figure shows a parallel circuit with 3 paths for current flow. Point A, B, C and D are connected to the same conductor and are at the same electrical potential. In a similar manner, point E, F, G and H are at the same potential. Since the applied voltage across between points A and E, the same voltage is applied between points B and F, points C and G, and between points D and H. Thus, when resistors are connected in parallel across a voltage source, each resistor has the same applied voltage, although the currents through the resistor may differ depending on the values of resistance. The voltage in a parallel circuit may be expressed as follows: ER equals to E1 plus E1 equals to E1 to E2 equals to E3, where ER is the applied voltage, E1 is the voltage across R1, E2 is the voltage across R3 and E3 is the voltage across R3. The current is parallel circuit divides among the various branches in manner depending on the resistance of each branch. See figure. A branch containing a small value of resistance will have a greater current flow than a branch containing a higher resistance. Kirchoff's current law states that the current flowing toward a point is equal to the current flowing away from that point. Thus, the current flow in the circuit may be expressed mathematically as follows: IR equals to I1 plus I2 plus I3, where IR is the total current and I1, I2 and I3 are the current through R1, R2 and R3 respectively. Now Kirchoff's and Ohm's law can be applied to find the total current flow in the circuit shown in the figure. The current flow through the branch containing resistance R1 is I1 equals to E by R1, which is equals to 6 by 15 equals to 0.4 amperes. The current through R2 is I2 equals to E by R2 equals to 6 by 25, that is equals to 0.24 amps. The current through R3 is I3 equals to IE upon R3, which is equals to 6 by 12, which equals to 0.5 amps. Now the total current IR equals to I1 plus I2 plus I3. IR equals to 0.4 amps plus 0.24 amps plus 0.5 amps. That is I total equals to 1.14 amps. In a parallel circuit, IR equals to I1 plus I2 plus I3. By Ohm's law, the following relationship can be obtained: IT equals to ET upon RT, I1 equals to E1 upon R1, I2 equals to E2 upon R2, and I3 equals to E1 upon R3. Substituting this value in the equation for total current, ER upon RR equals to E1 upon R1 plus E2 upon R2 plus E3 upon R3. In a parallel circuit, ER equals to E1 plus equals to E2 equals to E3. Therefore, E equals to RT equals to E upon R1 plus E upon R2 plus E upon R3. Dividing through by E gives 1 upon RT equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. This equation is the reciprocal formula for finding the total or equivalent resistance of a parallel circuit. Another formula of the equation may be derived by solving for RR, that is RR equals to 1 upon reciprocal, that is of 1 upon R1 plus 1 upon R2 plus 1 upon R3. So an analysis of the equation for total resistance in a parallel circuit shows that RR is also always less than the smallest resistance in a parallel circuit. Thus, a 10 ohm, a 20 ohm and a 40 ohm resistors connected in parallel have a total resistance of less than 10 ohms. If there are only two resistors in a parallel circuit, the reciprocal formula is 1 upon RT equals to 1 upon R1 plus 1 upon R2. Simplified, this becomes RT equals to R1 R2 by R1 plus R2. This simplified sort of formula can be used when two resistors are in parallel. Another method can be used for any number of resistors in parallel if they are of equal resistances. The resistor value of one resistor is divided by the number of resistors in parallel to determine the total resistance. Expressed mathematically, this becomes RR equals to R upon N, where RR is the total resistance and capital R is the resistance of the resistor and capital N is the number of resistors. I am going to discuss about the figure which I have given you, that is of series parallel DC circuit. The most circuits in electrical equipment are not series or parallel circuits. They are usually series parallel circuit, which are combination of series and parallel circuit. A series parallel circuit consists of group of parallel resistors connected in series with other resistors. An example of a series parallel circuit is shown, which I had given the figure. The requirement for the series parallel circuit are as follows. Number 1 is the power source, that is a battery. Number 2 is conductors, the wires. Number 3, load resistances. Load means resistances. Now number 4, more than one path for current flow. Now the fifth one is controller switch. And now sixth is safety device, or we say fuse. While series parallel circuit may appear extremely complex, the same rule used for series and parallel circuits can be applied to simplify and solve them. The easiest method of handling series parallel circuit is to break them apart and redraw them as equivalent circuits. The circuit in the second one figure which I had given is an example of a simple series parallel circuit that can be redrawn to illustrate this procedure. In this circuit, the same voltage is applied to R2 and R3, thus they are in parallel. The equivalent resistance of these two resistors is equal to the value of one resistor divided by the number of resistors in parallel. This is true only when the parallel resistors have the same ohmic value. If this rule is applied, the circuit can be redrawn as shown in this figure. This has converted the original series parallel circuit into a simple series circuit containing two resistances. To further simplify the circuit, the two series resistance can be added and the circuit can be redrawn as shown in this figure. Though the last redrawing of the circuit could have been omitted and the calculation done mentally, this circuit illustrates clearly that 125 ohm resistor is the resistive equivalent of the resistors of the original circuit. Now the figure which is this I am giving you, it contains a more complex series parallel circuit. The first step is simplifying the circuit is to reduce each group of parallel resistors to a single equivalent resistor. The first group is the parallel combination of R2 and R3. Since these resistors have unequal values of resistance, the formula for two parallel resistances is used, that is R E equals to E underneath, which is equals to R1 multiplied by R2 by R1 plus R2, that is equals to 120 into 40 by 120 plus 40, that is equals to 4800 by 160, that is equals to 30 ohms. Now then the parallel combination of R2 and R3 can be replaced with single 30 ohm resistor as shown in the figure. Next, the equivalent resistance of the parallel combination of R4, R5 and R6 can be determined using the formula RB equals to R upon N, where R small b is the equivalent resistance of R4, R5 and R6. R is the value of one of the resistors and N is the number of resistors in parallel. So RB B underneath is equals to R upon N, that is equals to 60 upon 3, which is equals to 20 ohm. The parallel combination of R4, R5 and R6 can now be redrawn as a single 20 ohm resistor as shown in figure. The original series parallel circuit has now been replaced with its equivalent series circuit. This circuit could be redrawn again to replace the 5 resistors in series with one 330 ohm resistor. This can be proved by using the total resistance formula for series circuit, that is R small r underneath equals to R1 plus R2 plus R3 plus, let it say RR equals to R1 plus R small underneath plus R B small underneath plus R1 plus R8. Then it will be equals to 100 plus 30 plus 20 plus 80 plus 100, that equals to 330 ohms. The first series parallel circuit used is redrawn to discuss the behavior of current flow. Like the parallel circuit, the branch currents I1 and I2 cannot be established using the applied voltage, since R1 is in series with the parallel combination of R2 and R3. A portion of the applied voltage is dropped across R1. In order to find the branch currents, total resistance and total current must be found first. Since R2 and R3 are equal resistance, so R equivalent equals to R upon capital N, which is equals to 14 upon, it was equal to 14 upon 2, that is equals to 7 ohms. Now total resistance is R T equals to T underneath equals to R1 plus R equivalent. Now it is equals to 21 ohms plus 7 ohms, which is equals to 28 ohms. Now using Ohm's law, total current is I total equals to E upon ER underneath, R is underneath by R is the T is the underneath RT. Now it is equals to 28 volt by 28 ohms, which is equals to 1 ampere. Now the total current 1 ampere flows through R1 and divides at point A with part of the current flowing through R2 and the other part through R3. Since R1 and R2 since R2 and R3 are of equal size, it is obvious that half of the total current or 0.5 amperes will flow through each branch. The voltage drop in the circuits are determined by Ohm's law. E equals to I into R. That is E R1 equals to I total into R1, that is equals to 1 into 21, that is equals to 21 volts. E equals to IR again, that is ER2 equals to I1 into R2, that is equals to 0.5 into 14 equals to 7 volts. Now E equals to IR, that is ER3 equals to I2 into R3, that is equals to 0.5 into 14, that is equals to 7 volts. The voltage drop across parallel resistors are always equal. It should also be recommended that when the voltage is held constant and the resistance of any resistor in a series parallel circuit is increased, the total current will decrease. This will not be confused by adding another parallel resistors to a parallel combination, which could reduce total resistance and increase total current flow. Thanks for watching, and I suppose that you will be like it, comment it, share it, and subscribe it. Got two videos on now in YouTube. The first one is aircraft maintenance technology instructions, and another this video I am going to upload in physics teacher, which will be common to both physics also as well as aircraft maintenance technology instructions also, because there is also a current and electricity to read in aircraft maintenance technology, and many things are very common which I had described earlier also in the video of basic current and electricity of aircraft maintenance technology instructions, and more videos to become of chapter current and electricity, that is basic electricity, and after that I will go for the alternators and generators, and these are all, as even now this electronic and communication system are also common to both of the channels. I have made videos on mechanics also in the aircraft maintenance technology, sound, mechanics of fluid. These all you can see through in this channel. I will be making separate more for physics teacher if required, because in this I have given the theories only. Now here I will be giving something practically, which are numerical based, something like that, because in that there was only that much required. Here I have to give more extensively than that videos. Many can go for the mathematics also as a simple knowledge about the mathematics in the aircraft maintenance technology videos, and if required I will be going to make another video for the mathematics and chemistry and bio and all. Now, grouping of cells. In general, a cell has a small EMF and small internal resistance. It therefore cannot supply large current to an electrical circuit. Hence, a number of cells are suitably grouped or connected to meet the requirement. Such a combination of cells is called a battery. There are three different ways in which cells can be grouped. That is in series, number 2 in parallel, and number 3 is mixed grouping. See, we will go for the storage batteries also, and here I am seeing these are the primary cells only. Secondary cells are those batteries, the storage batteries, that is a nickel, cadmium and lead acid battery. For that there will be another video. So let us see this primary cells, how they are connected in series. Now let small n cells of EMF small e1, small e2, e2 and so on till small en and internal resistance small r1, small r2, so on till small rl respectively be connected in series such that the negative terminal of the first cell is connected to the positive terminal of the second cell, and so on. Let this combination be connected across the external resistance capital R, and consequently current capital I flows through capital R. Therefore total EMF equals to ET equals to small e1 plus e2, small e2 plus small till plus small en. Total resistance RT equals to R plus in bracket R1 plus R2 plus so on till plus Rn. These are all small. Now therefore current applied by the combination I equals to small et by capital RT, that is equals to E1 plus E2 plus so on till plus En by R plus and bracket R1 plus R2 plus so on till plus RL, that is these are small. Now if E1 equals to E2 equals to so on till En equals to E, and R1 equals to R2 equals to so on till Rn, which is equals to small r, then capital I equals to Ne by R plus Nr. This equation is 35. Sorry, earlier was 35 and this is 36. Now there are some special cases. If capital R is very much greater than NR, then I equals to Ne by R, that is equals to N into current applied by one cell. B, if N multiplied by R, that is small n multiplied by R, is greater than capital R, then I equals to N small multiplied by small e by small n multiplied by small r equals to E upon small r, that is equals to current supplied by one cell. Thus current supplied by a series combination of cells is maximum when an external resistance is very high as compared to the total internal resistance of the combinations. Now the cells in parallel. No, I have not given the figure of series in cells in series. The earlier picture was given on cells in series. Now I am going to give you cells in